The talk today is on developing C++ APIs on top of Python, which you probably got from the description. There's a talk going on right now about how to be a better programmer, so I assume everybody in here is a great programmer, otherwise you'd be at that, which is really good. So just a quick story, really. There was a company that had a very successful C++ product many years ago. They still do have a successful product, and it had grown like many C++ products do to be very unmanageable, very unwieldy, and very large, several million lines of C++ code that a lot of the original developers had left, and nobody knew kind of how it worked. So they spent a lot of energy determining how they could kind of restructure things, how they could rebuild parts of the application to be more manageable, to be more accessible, extensible, all the great ilities that architects talk about nowadays. And they started work. They identified the kind of storage subsystem and they said, we can make this better. And they analyzed it, and they spent a lot of time developing a replacement storage system for all this data. And what they ended up with was essentially a giant green spun. They had reinvented parts of dynamic scripting languages, and they'd done it in a pretty poor way. And so they took another step back and said, well, this is really just, this is Perl, or this is Python, this is Ruby, this is any of these languages that exist today. Can we just try to use one of those? And they settled on Python. They said, okay, some of the developers knew Python, so they kind of plugged it in, and in a week they had replaced effectively a year and a half's work with a far superior system with better performance, more extensibility, all the qualities that we like about Python. And they shipped this, they developed products based on it, and they started letting Python kind of grow through the rest of their product sort of organically. They found extensibility points, they found plugin systems, all these ways that they could improve and replace the existing C++ with Python, all the time maintaining a working system, because this system, this application was there. So it kept the lights on. It was their cash cow. So they couldn't just let it not work for 2 years. And eventually they reached a point where their entire application, minus some critical performance parts, had been translated into C++, and into Python, and it was a very successful project. That is really the seed of what I want to talk about today: is how you can, if you need to, replace C++ code with Python code, but have it interact successfully with higher level, sort of executive level C++ until you can get rid of that executive level C++, which is an ultimate goal in a lot of these kinds of projects. I should say that story is half true, half of it's a lie. We haven't, that is my project right now. We've done half of that translation. We have replaced many of the guts of our existing application with Python, and it works beautifully. The rest we are aiming at, and that is my ultimate goal. This is kind of the metaphor, this geode, that I like. I've kind of searched and tried to find a good one, and it's maybe not geologically apt, but it's a very pretty metaphor where you have the outside, the ugly rock, it's the C++, and the inside is the Python, slowly making everything inside more beautiful until eventually, and this is where it's geologically not correct, but ultimately you would have a nice, beautiful crystal. And it's a pretty picture, so I thought I'd start with that. So I'd like to thank the internet for coming up with a great meme for this talk. I don't know if you guys like the juvenile humor I like, but this is real big on meme base right now. And this is the stuff I want to talk about, C++ calling Python. All right, so the main concepts, a lot of you are going to be familiar with this, and I'm going to try to go a little fast. My time is more compressed than I had initially thought. This is how C++ and Python normally interact. This is meat and potatoes for a lot of developers. You have some C library that you want to use in Python, so you wrap in some extension using whatever raft of technologies. You have all of these options are really good for this kind of stuff. This is, in my mind, one of the pillars of Python's strength, is that it can leverage all these existing libraries. You name it, it's been wrapped for Python. And that's made it a very widely useful language. These are all the sort of options you might have for doing extension development. And there's more. These are the ones that I know about and have used to some degree. This is sort of the next most common interaction between Python and C++, where you have some C++ application and you want to add a scripting ability to it. This is common in things like games or like CAD programs and stuff. They have some, big set of complex internal objects in their memory, and they want to let you poke around at them in Python. So they drop a Python interpreter in the middle and let you access a shell and write little scripts and things like that. This is fairly well supported. It's not nearly as common. It's slightly more esoteric than writing extensions. And these are the technologies I know about and have used for doing this. I'm a big fan of Boost Python for a number of reasons, and the C API. If there are other technologies for doing this, by the way, let me know afterwards, because I really don't know what they are, and I'm just curious. This is different from both of those in some significant respects. This is what the rest of the talk will be about. You have some C++ application, and you have some Python module, and you want to use that Python module fairly directly from your C++. How can you do that? You need to write this kind of wrapper layer. And what is the nature? How do you write that wrapper layer? That is what I'm going to talk about. And we'll talk about the reasons you might want to do that, the scenarios you might find yourself in, and how you can use this approach to transition from a monolithic C++ program into something much more Pythonic, something much more friendly, something you would want to program in rather than C++. I'm a big fan of C++, by the way, but given a choice, I will write in Python, and I would never start a new project in C++, but it's a good tool to have under your belt for certain things. The goal of these middle wrapper layers, what I set for myself when I started doing these, is I wanted to be able to expose the Python program, the Python module, with natural idiomatic C++ API. So something that a C++ programmer who knew very little about Python could approach and understand immediately. So something that used the C++ iterator idioms, or didn't force them to think about reference counting in some fancy way, that they could just use it very naturally and drop into their existing systems. And a good example the iterators are a great example. If you have good iterators in C++, you can use this API with the entire STL and with Boost and with all these other big C++ ecosystem components. And this is something you can accomplish for the most part. It's impossible to get rid of Pythonicness completely, and that's fine, because generally you don't really need to go that far. But there's ways to get most C++ niceties in these kinds of APIs. This is just an example. These next two slides are an example of what you might have in Python. This is very, very common Python code. You're just setting up your logging subsystem. Nothing fancy here, except, okay, this is a little bit fancy, but not terribly fancy. And you're just wanting to stream the standard out. This is how it can look in C++. And if you kind of just squint your eyes a little bit, it's the exact same code, minus the necessities of C++, the include and the avoid init logging, that kind of stuff. But you can see I have a basic config call. I can get a logger and drop it into a logger object. I can add handlers very naturally. Here is maybe the part where Python sneaks in a little bit. I have to use some import calls to import the sys module and access an attribute standard out, but drop that into a stream handler. Beyond that, it's very much the exact same code. More brackets and semicolons and things like that. And even this kind of stuff, this import, if you need to, that can all be sort of abstracted behind more APIs. This is a very bald way to get at the Python subsystems. So this is the flavor of what I'm aiming for. I can have some C++ program. This could be in my my main.cpp, calling all this stuff while it's initializing the rest of the C++ system as well. And it's very directly just calling that into Python. And that's very nice. And you can do this with all sorts of other modules. Logging happens to be a really good example because it's something that's intuitively easy to share across the language boundaries. If I use my Python logging throughout my C++ application, I suddenly have this great big nice unified and very powerful logging system available to all of my systems. So I said I was going to talk about motivations a bit, why you would want to do these kinds of things. I feel like maybe I don't even need this section. And why would you rather write in Python than C++? You probably all know the answer to that. But we'll talk about it anyways. One is just you want to be able to write in a language that has more expressivity. It's much more productive language to write in. And if you can remove the barrier, the conceptual barriers between calling one language from the other, then you can write as much code as you want, or as much code as you're sort of able to in Python, and just let C++ do what it has to do. So this is a really big motivating reason why you might want to use the kind of techniques I'm going to talk about here. This, of course, is related. The edit, compile, run, debug cycle that all C++ developers live in. It's our burden to carry. Big coffee break up there, because that's what compiles become in a lot of big C++ systems. You push the compile button and you go, grab some coffee, go home for the day sometimes because it takes several hours maybe to build. If you can remove this compile cycle, the compile component of this cycle, and just get it down to edit, run, debug, that's a much quicker development cycle, and it's a much more productive development cycle, and it keeps your mind in the zone. That's another problem with compiles, right, is that they take you out of whatever you're doing, wherever your brain was at the time you push compile. You have to sort of stash that away, drink your coffee, come back and push it back up into cache. So, like I said, this is related to the previous one. It's just a question of productivity. It's a question of being in a good development environment. And if you can get rid of the compilation phase, then you're gonna gain a lot. This is kind of what we talked about with logging earlier. If you have this ability to call Python from C++, suddenly you have access to everything that's written in Python. This is the inverse of the writing extension modules approach that Python benefits from. This is allowing C++ to use whatever Python modules you want. These are examples that I think are really illustrative. Logging I mentioned, UUID, regular expression matching. Template engines are a really good one because Python has a whole boatload of really good template engines. C++ maybe has some. I've never tried to find them, never tried to use them. I'm sure that if I found them, they would be about 3 or 4 times as hard to use as anything in Python. So if I can expose a good template engine API up into C++, I can use whatever I want down in the Python end. And that's a real win. But this is the sort of overarching reason. I have an existing body of C++ code that I have to live with for whatever reason. And I put this link up, Working Effectively with Legacy Code. This is the reason that you need to use these techniques, is you're facing the issue where you've got an existing C++ application. Sorry if my monitor's freaking out here. But you want to start replacing parts of it with Python. This book is fantastic, by the way, if you haven't read it, and you find yourself dealing with lots of old C++ code. I highly suggest it. But if you're sitting at work or doing whatever projects and you say, I hate doing this C++, I wish I could replace it with Python, hopefully I can get you on the path to that. I'm not going to be able to present the gory details of everything you're going to need to do, but I want to get the seeds in your mind of where to look when you start to think about how do I handle exceptions coming up from Python? How do I translate types across the boundary? I want to lay down a high-level map and give you some details about how to do that. And hopefully these techniques become more widely understood, because like I said, this is a fairly underserviced part of the Python ecosystem, and for good reasons. I think there's a sort of natural progression from starting with a C++ application or some library perhaps, and transitioning it into Python. This is the kind of picture I showed earlier. I have a C++ application. It calls a C++ library. This is how a lot of the world is run right now. This is just the sad state of software. This we talked about earlier. Now I can move to this model where I have a C++ application calling through a C++ wrapper down into Python. Okay, this is a really good step in the right direction. All the debugging I have to do for this, I can do much more easily. All the development I can do much more easily. It's more fun to write, more productive, etc. But it's still not all the way. I haven't replaced all the important bits. This is sort of the next phase, as I see it in a lot of development that's going to go this route, is now you've replaced the main, and you're going to have to rename that, of course. You can't call it main in a library, but you can replace the main, the executive level, your event loops and that kind of stuff, initialization, with Python code. And that's wonderful. That's another sort of burden off of your back. Now you're developing much more in Python. It's easier to debug, easier to reason about in a lot of ways. You don't have to worry so much about static initialization problems that you face in C++, for example. There's another really interesting reason that you want Python at the top, even a very thin Python layer at the top that we'll talk about later. It has to do with debugging. But having that, even the thinnest possible Python layer at the top gains you a lot. It gains you testability, gains you productivity, gains you debuggability, and we'll get into that a bit. And of course, and I guess it's worth pointing out that when you get to this point, where you've got Python wrapping everything and you have these extensions now, extensions are much easier to write. They're much more well understood, much more well supported. That slide I showed earlier with 10 or 15 technologies, you can use all of those, any of those, whichever ones you want, to write these extensions versus these sort of 2 limited options that I know about for doing the reverse. And of course, this is where we want to get. And this is where we would all like to be, ideally. Python application using Python packages and modules. Of course, there's always going to be, well, I say always, very often there's C kind of down in here somewhere, NumPy or some other important package written in C that you have down there, but your view, your mental model of your software is all Python at that point, and that's a really great place to be. So if you follow this progression, I think you can get there. Even if you stop here, which I think would be quite natural for a lot of people, even if you stop there and say, there's certain things we have to keep in C++. This gives you a way to get there and to maintain those in a sort of extrinsic way, maintaining this functionality extrinsic from the application rather than having it be everything, every part of your application. Right now, doing great on time. Okay, so at this point, I hope you kind of understand if you be able to recognize if you're in a situation where you need to use these kinds of approaches we're going to talk about, and you kind of understand where I'm coming from. The rest of the presentation effectively is various techniques for doing all the kinds of things you need to do to make the languages work well together, coming from Python up into the sort of executive C++ level. So this is very, very common sense. But it's worth mentioning. You have some Python module, myPackage, that you want to expose through a library, libmypackage.so or .dll, depending on how you swing. I don't think there's anything terribly controversial about that. This is just a naming convention, effectively, so that you remember when you see libmypackage, you're really talking down to myPackage. Along with that, I think it makes a lot of sense, and I've been really happy with this, is that you use a namespace in that library called myPackage as well. This way, you basically do this so that you don't have to think real hard about what part of the code you're looking at. Anything in the myPackage namespace or in libmypackage.so is calling down into this Python package that you want to access. So it's just a packaging issue. How do you just keep yourself sane? How do you remove cognitive load while thinking about what can become a very complex stack of software with Python calling C++, calling Python, calling C++. Coupled with that, you have questions of package initialization. And in Python, you don't have this problem so much. In fact, you have a very graceful system for dealing with initializing stuff, because when you import, you can run arbitrary code, and it's run at a very specific time, very specific order, et cetera, et cetera. C++ has a half-assed version of that, right, where if you're not careful, you can try to use static initialization to set things up in very complex ways, but you can also do a great deal of damage, or you could have everything running on your development system, and on your production system it could just go to hell because there's not a defined order. So you end up relying on having initialize calls very often in these kinds of libraries. And they don't necessarily have to exist, but if they exist, they generally do things like importing the package from Python that you want to access attributes and elements of, and then registering type converters, maybe registering specific exception translators, and we'll get into these techniques in a few slides, as well as anything else you want to do, setting up loggers, whatever you want to do when you initialize your libraries. You generally end up with something like this, and it can be more complicated than this, but having an initialize function generally makes a lot of sense when exposing Python. So one of the big questions that we get, especially if I get a junior developer working on something like this, their brains think of Python, their brains think of C++, and there's kind of a void in the middle, and they have trouble conceptualizing how to transport types across, how to transport objects across this boundary. And it can get confusing. If you spend too much time developing complex systems with lots of loops and stuff in them, then you can confuse yourself even if you're really good at this stuff. And what I try to pound into their heads, besides common sense, is just to remember that everything in CPython, and be very clear about that, is a Py object. And a Py object is just a C structure. And if you can get a pointer, if you can get that Py object pointer, then you can stop thinking about Python and start thinking about C. You don't have to maintain this dichotomous world. And I think once they understand that, once you can really build it into your brain that Py objects are just the things that you're working with in Python and vice versa, then all the voodoo disappears, and there is no more magic at that point. It's just, now you start to view Python as a runtime library rather than a language. You start to see it as a sort of little very powerful object system that you can use to access all this neat functionality. And you start to see it as a C library and think of it as a C library rather than as a language and an interpreter and a REPL and all that kind of stuff, which is what people generally come into Python with conceptions of it as. So it's a very simple model that works for most types, not all types, but that works for a great many types, I should say. In C++, I just have my class, however I want to define it, with its API. And one of its private members is, sorry, I should clarify. When you see BP, it's Boost Python. I've shortened that. And a Boost Python object is not much more than a friendly Py object. It does reference counting and things like that for you. So this is a C++ class holding onto a Py object, which is down here, managed by your Python runtime. And this model really captures a lot of what you need to know about translating data across the boundary. When I pull a Py object up from Python and it crosses into C++, I just wrap it in one of these, and when I pass it back down, I just extract that Py object and use it in the Python code. And I'll show you specific techniques for doing that. But this model really covers the vast majority of complex objects. Simpler objects, sort of value type objects, you might just end up copying data out of the Py object into your C++ class and then doing that copy back. But for something big like a NumPy array, for example, if you got 20 gigabytes of data, you don't want to be copying that, of course. You want to just pass a pointer to the array object out. So this model, like I said, works for most things. So the actual mechanics of how you get the objects back and forth, it all comes down to, well, it depends which direction you're talking about. In this case, we're looking at the Python to C++ direction. So I have something, or say a return value coming out of a Python call that's going back into my C++ level. I need to figure out what kind of thing to turn it into. And the way to do that is very Pythonic, is you use type checking, use introspection. I should have used introspection instead of inspection on this slide. But obj, can you see my pointer at all? I'll point. Obj is the thing that you're trying to figure out what to do with. Class obj is some class I want to compare it with. Is this a UUID? Is this a foo? And if it is, return a new foo. Right? You replace t with whatever. Often this is done in kind of a templating system so that you end up with, or you reduce your code duplication. But once you've determined what kind of thing obj is, then you just construct the C++ class that you want. So this code is being run in sort of the boundary layer, the DMZ between Python and C++. Yeah, it's a scary place. But basically you construct an object around it. This is Boost Python code for constructing handles that do the handles and objects that do the reference counting for you. And so what I've done is I've passed a Boost Python object to the constructor of a T, and I'm going to pass that T back to the C++ level, and now my C++ can do whatever it wants with that Py object. It can call functions on it, it can check its properties, etc., etc. That is how you get from having a Py object in Python up into C++. Like I said, this is a small snippet of the code. This is sort of the heart of how you do the translation from Python to C++. This is going to be part of some larger system where the call mechanisms are going to say, okay, I've got an object, I want to get it to C++, and it goes through some registry of type checkers and converters and things like that. But this is at the heart of it. And if you can keep this model in mind, then this should make sense. All you're doing is wrapping the object in a C++ thing and passing it back. The other direction, passing something from C++ down to Python, of course, can't rely on type inspection. You have to rely, well, you could use RTTI if you're brave, but that's, I don't really suggest it, and it's not really necessary. You can use a template system to register converters. This is how Boost Python works. Or you can roll your own version of this, but I suggest using a pre-made one. Something that you basically say, if I want, this convert function is invoked for objects of type T that need to get down into Python. So at the calling level, this gets called somehow. All it does is take that T, whatever that thing is, extract the pointer, the Py object pointer, increase its reference, and return it. And now, when it comes out of this function, CPython can use it all day long. And it's been increft and decreft properly, and all lifetime management is all taken care of for you. And that's how you get things from C++ down to Python. Now, I mean, these last two slides obviously are, they follow a single pattern. They follow the pattern where I've got this kind of layout of my objects. But but it never really gets much more complicated than that. If I had a C++ class, and if I was doing sort of value type across the boundary, then I would be doing more work in here, more copies of objects and ints and floats and stuff like that, but nothing fundamentally more complex. Really, you just want to be able to, you have to tell the boundary layer, for C++ objects of this type, call this function to get it into Python, and when I'm coming out of Python, tell me how to inspect objects to determine what to do with them to get them out of Python. And you can glue this all together. Memorize this. No, I'm kidding. You're not going to memorize this, but this is the Boost Python method for setting these things up. You can push back these registry things at the top. You can register your 2 Python converters, and then so ignore everything from there up. Once that's done, this is how you get things out in C++ land. You have some Python object. You want to extract it to a my type, and it comes out as a my type X, or it throws an exception saying, I don't know how to do that. And then to pass X back into Python, I have some Python class, Python object, whatever, look up an attribute, a function called doIt, and I pass X in. It's a very natural way to do things in C++, and it maps directly onto Python. And these 2 functions effectively enter what I called the DMZ earlier and do all of this analysis of objects to figure out what to do to get things back and forth. This stuff is not very well documented on the internet, really. I've got some links that I can give you, but this is an area of C++/Python development that could use a little bit of love. But it's very powerful, too. Hopefully we'll see more of that as we go. I'm good on time. The next big stumbling block for these kinds of APIs is exceptions. So I'm in C++ and I call down into Python. Some work happens and an exception is thrown. Now in Python, of course, an exception is really just a couple of entries in the Python runtime. There's a couple of pointers that are set to tell you this is the thing that was thrown, this is its type, and this is the traceback. Maybe you get a traceback. And to deal with that, you have to, this is a sort of bare bones way of dealing with it. You made some API call, you check if an error occurred, and if so, you do something. You make your next call, you check if an error occurred, maybe you respond to it. And that is fundamentally how you would do it in pure C. And that's awful. I mean, that's no fun to write. It's very error prone. It obfuscates the code, especially when you're thinking in terms of Python and C++, which have exceptions, and all of a sudden you're thrown into, sort of 1970s land. And yeah, so you want to get away from that. How do we make it more natural to translate exceptions across the boundaries? Well, Boost Python, again, helps you out with this. I'm pushing Boost Python because I know it very well, and I think it's a very powerful tool for these kinds of things. But again, other technologies exist, and you can roll your own kind of solutions. But one of the really nice things Boost Python does is when you're coming out of Python back into your C++, so the thread of control is returning up into C++, it checks, has any exception been thrown in what just happened down in Python? No matter what just happened, it checks. And if anything happened at all, any exception, it always throws one of these, a Boost Python error already set. That's its sole way of telling you an exception was thrown. And okay, that's much better than having to check, make all these little function calls and stuff like that. You get a very uniform, common sense way of dealing with exceptions. At the same time, it doesn't tell you what happened. You're stuck saying, okay, I know something bad happened, so I can just throw an exception. Or log something and carry on. So the next step, of course, is how do I get from knowing an exception was thrown to actually responding to it in a sensical way in C++. And, well, of course, a bit of that comes down to thinking again about how does the Python C API work. Well, you can use pyerrorFetch to figure out, okay, what happened. And that will return back to you either something happened, it was type, value, and traceback, or it can tell you that nothing happened. This code is actually trimmed down. It would not work in real life, but fundamentally it's correct. Assuming that something did happen, then you can check what happened with given exception matches to see, is it a value error? Is it a type error? Is it an index error? Whatever. And then based on what you find, then you can throw your C++ exception. So this is the guts of an exception translation system that says, something bad happened, I want to find out what it was, and if it's a value error, throw a C++ value error. If it's a type error, throw a C++ type error, or whatever you want to do. The point is that now you have the keys to make your C++ API act in a very C++-ish way and have it correspond very strongly with the Python API. Yes, you can. So if TB comes out of this PyAir fetch, that's the traceback. And it's just a Python object, right? You can hold on to that. You can stash it away in your exception that you throw. I mean, you can do whatever you want with it as long as you keep the incref correct. Boost has an exception class that lets you tag stuff onto the exception and then kind of rethrow it, and that's a great way to attach this kind of information. And you can get really beautiful stack traces, actually, of C++ and then a Python stack trace, and then more, and it's sort of approaching nirvana at that point because suddenly you have this uber debugger in a sense. We'll talk about that in a bit, actually. But yes, you can hold on to it. I should say, though, if you start monkeying around with code like this, be very aware that a lot of Python C API calls clear these exception registers underneath you. So you have to be very careful about making sure that you grab pointers and incref them and stuff like that before you do anything after PyAir fetch. Otherwise, it might get cleared, or you might end up with an invalid pointer or something like that. Really, that comes down to reading the C API and paying close attention. So finally, you can get to a point where you have code like this. I try some Python function. I catch error already set if it's thrown. And if it is, I can just call a function that translates whatever the extant exception happens to be. I should point out, Ackward is a library that implements a lot of this kind of stuff. It's on Google Code if you want to see it, but it exposes a lot of the standard library, parts of the standard library. Like there's a complete wrapping of the logging library, a complete wrapping of UUID. Sorry, I keep touching that. And a number of other things, but it includes exception translators in the mix. So that's the long and short of how you do exception management. It's not difficult. It's kind of a hassle until you have a good system in place. Sort of the third leg. I'm sorry. The sort of third leg of, in my mind, of these APIs is how do you manage iteration? And at first it seems fairly difficult because you have the sort of Python notion of iteration, which is construct an iterator next until it throws, versus versus C++ where you have begin and end, and you're doing your sort of comparison between begin and end. Ultimately, though, it's actually very simple. You just construct your C++ iterator to, of course, hold on to the Python iterator and call next to get the next value out, but make sure that next call catches stop iteration. And when it does, sort of mark the iterator as at end, so that now you can treat it like a normal C++ iterator and go back and forth. Thanks. Go back and forth with it, and it works very naturally. One big distinction between the two types of iterators, of course, is that Python iterators are, in C++ parlance, they're forward iterators only. You can't there's no random access. And so in C++, you're kind of used to having iterators that can kind of bounce around inside a vector or something, but in this case, you end up with just a single style of forward iteration. It's not a big deal in general because you're trying to mimic a Python API, which is never going to have random access iterators, so you end up not worrying about it too much. I feel like this is a poor description, but I think if you sit down and write an iterator with these things in mind, you'll find that it's actually very straightforward and kind of trivial. In fact, you can write templates that sort of do it all for you. You can have an iterable template that provides an iterator that you can just kind of drop onto any C++ class that you need to, any container type. And it's very, very simple. Static typing versus duck typing is one of the this is one of the sort of things that people do not or do like about Python, or do not and do like about C++. And it is, of course, one of these, I hate the phrase, but impedance mismatches between the languages, right? In Python, of course, all of these could be conceptually the same class in the sense that they expose the same API. They're intended to be duck typed into the same functions, but they may not share actually any type relationship. They may not be subclassed off of anything. And that works just fine in Python. But in C++, it absolutely does not work. You have to sort of divine and understand the subclass relationships between things if you want them to work properly. So if I've got these down in Python, of course, I can pass any one of these types into a function that accepts whatever their logical base class is. In C++, I have to figure out what that is. I have to design that base class and write all the APIs that would accept these using that API or using that subclass. And it is a bit of a pain, but it's also a really great exercise because it forces you to figure out what your base classes are in a sense. It forces you to figure out your ABCs in Python. And so it's sort of a fun exercise to do if you are doing this kind of work. I wouldn't do it unless you had to, but It's a bit enlightening. And one of the kind of beautiful aspects of it is that I can write this my package database thing to work with any of these and any other type that ultimately ends up having the same API, because the only real relationship between the C++ class and your Python classes is a bunch of string names, because of course everything in Python, you're just looking up strings in a dictionary to call functions, to get properties, etc., etc. So my package database becomes this basically thin proxy layer over anything that exposes the correct API. And so you build new Python classes that do this, and your database class up in C++ will continue to work. I kind of stress this a little bit because people's, again, a lot of like junior developers who come in and start working on this stuff, they get really concerned about this, or like, how do I map my C++ onto my Python? Once they do it a few times, though, they find that there's no magic. It's really quite easy, and yeah, it's just string name lookups and things like that. Other stuff. There are, of course, many, many other things that we don't have really time to go into regarding these APIs. Enumerations are one. Of course, Python doesn't really have those. Constness can be a real bear if you're a really const-oriented programmer in C++, which you ought to be. You end up writing special handles, smart pointer kind of things that manage const pointers rather than const objects, and that's how you can make that work. Properties you can expose if you want, or you can just have them be getters and setters in C++. Tuples, fairly straightforward. Keyword arguments, I generally steer away from those in C++ because they're kind of unnatural in C++, but they can also be emulated. Subclassing, you can write in C++ subclasses of Python classes. I've never found a great way to do it, nothing that satisfies me, but it can be done if you absolutely need to do it. Acrid has a way of doing that with logging handlers, I believe. You can subclass logging handlers in C++, and it works. Lifetime management, that's really just comes down to managing your PyObject pointers and making sure that you incref and decref at the right times. I didn't go into detail on these because you'll figure them out as you go. They're less rocket sciencey than the other ones. We have some time. I'll try to go through some of the interesting bits. We were talking about this earlier. Debugging the full stack. Can I get, if I have my debugger attached to, GDBs attached to my C++ application, can I see these stack traces? Yes, if you have the right tools. If you have a stack trace object and you have the GDB with the new Python extensions, you can examine that and print it out. That works very well. These are just a number of tools to allow you to approach this problem in different ways. PDB set trace, of course, dumps you into the debugger. And if your environment is set up right, you can actually then interact with the code that's being executed in here, even though that's what's running at the top. The GDB Python extensions are fantastic. If anybody here is working on those, thank you. They're really, really solid. Colleagues of mine have had good luck with Visual Studio. The new Python support in that is supposed to be quite good. A good trick to know, calling sigint in your Python code, or triggering a sigint in your Python code will kick in your C++ level debugger. That's a good tool to have if you are trying to sort out where some bug is happening. It's a way to set breakpoints. It's kind of like PDB set trace, but for your C++ debugger. Common logging. I talked about how you can use the logging module that's implemented in Python all through your C++ stack, and this is a way to do fairly reasonable debugging. Debugging individual layers, this is where Python really shines. It's very easy to run, in general, a Python module on its own, or to add some stub code that calls the right things. So that's a good technique. But we talked earlier, I was mentioning way earlier about replacing your main function with some small Python shim, and this is why you would want to do that. You can't attach PDB to a program when it's running. You can do that with GDB, so there's an asymmetry between the debuggers. So if you have this the thinnest imaginable layer of Python at the top of your code, suddenly it's a Python program and you can start it under PDB, and now you can have two debuggers attached at the same time, and this actually works really well. This is how you get some of these sort of beautiful stack traces, and you can really understand what's going on in your program. Attaching PDB is something I've wanted for a long time. It's a shame we don't have it. Well, maybe it's not feasible. And I would be remiss not to talk about performance. This is something that people will immediately mention when you say you want to write code in Python when they're used to C++. They'll be worried that it's going to slow everything down. If you do things wrong, of course it will. If you have some inner loop that's calling some function that your C++ compiler is, unrolling and inlining, that's going to be really fast versus what Python is going to end up doing, which is calling a bunch of functions and slowing you down by a factor of, 2 orders of magnitude. In general, though, it's not an issue. In general, I think that most of you are probably aware that, the kind of the Pareto principle applies. 80% of your code can be pretty slow because it's not being called all the time. This 20% of your code that needs to be fast, maybe it has to stay in C++, or maybe you have to think about how you're writing it in Python in a different way. But cover this slide up and say, just don't worry about performance that much. In general, my experience has been that you can basically translate your code, get it correct, test it, and then make it fast enough. And just using Python is not what's making your code slow. It's not understanding your code, which is making your code slow very often. So be aware, but don't be too scared. That's what that slide should say. All right in time. These are a few references that you might be interested in. Boost Python documentation, I think 149 is the latest Boost if you want to learn about that. Unfortunately, the Boost Python documentation for what we were talking about in this discussion, in this session, is not very good. You have to do some spelunking and archaeology to understand how to do coming up from Python into C++. That's a not very well documented or exercised level of the code. Awkward is this library I mentioned that uses a lot of these techniques to expose parts of the standard library. There are some blog posts about some of the type conversion and exception translation technologies that I talked about in here. And I believe that's about it. Yeah, this talk is available. It's on Google Drive, I think it's called now. It's public, so if you want to find it, you can. And we have 6 minutes for questions, if anybody... Oh, 6+ minutes, so yeah. Yeah.
So you say you started off with some millions of lines of code, and then basically you've been working on a rewrite of that into Python.
Just a second. Can you please repeat that?
Yeah, of course. Of course, yeah.
So you're saying that you had started off with some million+ lines of code of C++, and then you've been rewriting this into Python. So you have some idea then of how much code savings?
Yeah, so the question was, since I'm doing these rewrites of C++ into Python, what is the code savings? I guess lines of code is one way to measure that. Sort of cognitive load is another. In terms of lines of code, we don't have a great number for you because the original system was so bad. It was sort of so intertwined with everything in the code that we don't know what we knocked out. We don't know what was unnecessary originally, et cetera, et cetera. My intuition is a 10-to-1 savings. And when I'm writing the Python code and I think about what I would have had to do in C++, I imagine about 10 lines of code for every Python line. And that's a huge savings. Of course, that's a guess in a sense. Well, no, we've translated a small part of a very large application. So last time I did an SLOC was something like, I want to say 35,000 lines of Python out of an application of 2 million-ish. So you can imagine we knocked out on the order of 100, 200, 300,000 lines of code, which sounds about right. And it's much easier to develop. That's a gain that can't be underestimated, is that once you have this code in Python, it's easier to access, it's easier to debug, it's easier to play with and modify, et cetera, because the compile cycle is out, and that's a big win. Yeah. Yeah? Yeah, so the question was, are there special idioms or techniques for testing the translation layer, the layer that goes between the languages? Yes, but they're not going to blow your mind. I mean, basically, we have unit tests for the translation system itself. So we have some dummy types that we go back and forth and check their data to make sure that the int was 4 here and it's 4 over there. The best approach that I have for testing instances of those, so I've written some C++ class that's part of the production system, and I want to make sure that it's doing the right thing, is I just have a function call I just have a test for every function call, everything that I know is crossing the boundary, just to make sure that it doesn't throw a attribute error. That's the biggest thing, is you've mistyped the function name, you've mistyped the attribute name. So really these are just simple smoke tests, but these layers are really thin. In fact, they're automatable. Ackword has a code generator that you can give it a description of the Python and it spits out pretty good C++, and so you don't have to worry too much about it. But yeah, it's pretty simple. Yes?
Are you using CPython in order to call the Python code from the C++ application, if I understood correct? No?
Yes.
Then, how many interpreter instances are you running? I mean, one per thread, one per module being replaced, one per application?
Right. So the question was effectively how many instances of CPython am I running inside my application? Right now we just run one. We don't have a need really for more than that. Most of what we're doing in Python right now inside this application is data loading and saving, and that's being done through a database effectively. And we don't need multiple threads. Haven't thought very deeply about how I might manage more than one interpreter at a time, or if I would ever need to. It's an open area, frankly, for me, because I know that we're going to face it eventually. As this application becomes more and more Python, those kind of questions will come up. My gut tells me I'll end up using subprocess quite a bit. A lot of what we want to do is long-term job calculations and stuff like that, and numerical things, and we can just spawn those off into another process and not worry about. I mean, multiple interpreters in a single namespace, a single address space, is going to be problematic because there's all sorts of statics and stuff in Python, so you'd have to somehow manage that. And so subprocess just makes that problem disappear. I think your hand was up first, yeah.
Have you looked at integrating with the other Python interpreters?
Not deeply, but it's something that keeps me up at night, because I know that, okay, I mean, we are very heavily, leveraging, what are we on time? CPython, of course, we're bound to that. So if we ever want to move to PyPy, what is that going to mean for us? We're very reliant on things like NumPy as well. So until the rest of the Python universe moves, we're stuck where we are anyway. We have looked at Jython. That's important for us for business reasons, and it seems doable. And we looked at .NET, IronPython, and that seems doable as well, but we haven't done a lot of actual research and sort of production level stuff with that at all. I'm sorry, I forgot to repeat your question. Are we looking at alternative implementations of Python? And you heard the answer. So, yes.
Post is a very large library and has a lot of overhead Python.
Yeah.
You analyze some other libraries as Spoken from PySide or something?
I have not looked in depth at Shiboken. I've looked. So, we had a slide here at the beginning that talked about some of these. Basically, these are the only two ways that I know to do everything that I'm doing now, and Boost Python makes it so easy in many ways. If Shiboken or Swig or any of these other tools is appropriate for doing this kind of work, I would love to know, and in fact, if you have ideas, please let me know. But these are really the only two ways that I can think of to do it. Everything else is very much geared towards taking C and putting Python on top of it, not the other way around. Boost Python just does both directions very well. You're right, though, that in fairness, Boost Python is a very heavyweight library. The compile times that you get with Boost Python are tremendous because it uses all the template metaprogramming magic in the world to make itself work. But the convenience, in my mind, is worth it. And if you have a good build system and good dependency management and stuff, it's less of a problem than you might think. Yeah. Anybody else? All right. Oh, sorry. Yes.
Out of curiosity, what was probably the most complicated part, or was there any research you found that was complicated moving C++ to Python?
I mean, on a pragmatic level, it's educating developers. We have, a building full of people who've been doing C++ for their careers, and convincing them to learn Python and like it was an effort. Once you get them to do it, they love it. But it's a mental jump. From a technical point of view, I'm just going to give you the purple smoke answer. It's understanding all of this stuff. It's making all the dots connect properly, because what I started calling the DMZ, this zone between C++ and Python, is very mysterious when you first approach it, and you spend a lot of time thinking, okay, how do exceptions work across that? How do types get translated? And how do I make that system work in a seamless way so that my developers aren't constantly thinking about this? And it's making it smooth and making it, I guess, low friction was the hardest part. The single most difficult technical detail was probably exceptions, largely because it took me a long time to make sure that I wasn't invalidating pointers to exception types and stuff like that by calling other Python C API calls. That was that was touchy, and it was a problem because you would think you had everything right, and you'd run your program, and it would just crash in a mysterious way, and you'd spend half the day tracking down pointers and trying to find where you were missing your, where you were not decrefing or increfing or something like that. Yeah. But hopefully I got that all taken care of. So, yeah.
Okay, so talk is finished, and the next one will be about possible and how to pass the
All right. Thank you.